Hi, so today we're going to be talking about Module 2, Lecture 1. So here I have Module 2. Let's get the lecture slides out. This is Module 2, Lecture 2. We get the lecture slides out. So this is going to be more of a kind of theoretical, I wouldn't say theoretical, it's just more of what is hypothesis testing and what are confidence intervals. You've probably seen this in the last class. So this is just going to be an introduction to that. And then the next two lectures, we're actually going to be using R to produce some of these things. So this is kind of the math behind it, just to give you kind of a high level understanding of what's going on here. Okay, so recall, right? We discussed that for a random sample, X1, Xn that you could collect. So in the example of heights, right? I go get a bunch of heights of kids and see how much they grew over a year time span. We have G is a function of this, and it gives you a sample statistic. So like the mean, for example, is just the average of all the points. It's a function of your data, right? You plug in your data, you get a mean. Same thing with the variances. You plug in your data into this variance function, which would be in place for G, and you get a variance. Same thing for medians and same thing for proportions, right? Using indicator functions. So in hypothesis testing, we use different functions to test hypotheses about different population parameters. So these population parameters are, indicated by different things. You might see pi, mu, gamma, sigma, whatever. So for example, mu is the true population mean. So in the example that we're talking about, as far as kids growing from 7 to 8 years old, we assume, right, that there is some true average rate in real life, like it's decided by God or the universe or whatever. We call that thing mu, okay? And we want to estimate mu. A good way to estimate mu is to go get a bunch of data and take the average. Okay, that's an estimate of mu, okay? And we can use that estimate to test whether, the mean, the true population mean that guides the universe, right, from 7 to 8 year old growth is 2 inches or 1 inch or whatever. We also can make inference and test hypotheses about pi, which would be a population proportion. For example, right now we're still deep into COVID, right? This is still a pandemic. And maybe you want to look at, what is the risk of death in patients given that you get COVID? Or what's your risk of long COVID? And so to get that, right, you might go follow up with patients that have been admitted to the hospital with COVID and record the proportion that had long COVID or something like that. And you might test, hey, is this risk of long COVID or death more than 2%, more than 5%, more than 1%, whatever it is, right? You're going to test hypotheses based on this. So in general, what we're going to do is we're going to let theta here for the next couple slides denote a generic population parameter. So it could be mu, the mean, could be pi, a proportion, whatever. Don't worry about it. Theta is just a stand-in for any kind of hypothesis test that you could be doing. So here's the height gain example. Remember just how to read this data. First row observation is I equals 1. That kid's name is Greg. The kid Greg grew 2 inches. Second row is Jared. The kid grew 3 inches. Diane grew 4 inches. Jenny grew 1 inch. Charles grew ½ an inch. So maybe we want to test mu, which is the true population mean height increase from 7 to 8 years old. Now, we never actually know this, right? You don't have a dream and the universe or God or whatever tells you, hey, look, I'm going to tell you right here, on average, in perpetuity, kids are going to grow by 1.5 inches. Okay, we don't know that. We'll never actually get that information, but we can try to estimate that mean by actually going and collecting data. And that's the whole point of statistics, right? We're trying to figure out things that guide processes in the universe or human behavior or whatever based on data that we have. So we're going to first set up two competing hypotheses for hypothesis testing. A null hypothesis, H0, is what we assume to be true. For example, we might assume that the mean height is 2 inches. We assume that. All the formulas on statistical tests are based on your null hypothesis. An alternative hypothesis, H1, is what we choose instead of H0 if there's enough evidence to say H0 is true based on the data. H0 and H1 together represent all possible values that theta can take. So as an example, right, maybe I assume that the, mean true, the truth, right, true mean height growth of 7 to 8 year olds is 2. Okay, that's my null, i.e. H naught mu equals 2. And maybe we also assume in terms of our other ones, our alternative hypothesis, let's say null, alternative. Maybe the alternative is that the true mean height growth of 7 to 8 year olds is not 2, which can be written as H0 mu not equal to 2. Okay, so if I go out and collect a bunch of data, let's say I go out and collect 1,000 heights, and I get an X bar equal to 2. That's pretty consistent with the null, right? Let's say instead I get an X bar equals 6. Okay, that suggests that the true mean height growth is much bigger than 2. Okay, so the whole idea about hypothesis testing, but is it that much higher? So we have to kind of impose some things behind it. So the whole idea is, hey, we want to test, is the mean height growth 2 inches? So we're going to go and collect a lot of information. We're going to go and collect data. And we're going to use that data. We're going to plug our data into this G function, which is going to give us a sort of level of evidence of this null hypothesis. Okay, so here's an example. We could do a one-sided test. That was a two-sided test that I wrote, but maybe we want to test, is the average growth of mu bigger than 2 inches? So you could test this. The null would be, you'd assume that the average growth is less than or equal to 2 inches versus it's bigger than 2 inches. So when we do a hypothesis test, we either don't have enough evidence to reject the null. That means that, we can still kind of assume the null is consistent, or we have enough evidence to reject the null in favor of the alternative. Here, rejecting the null in the favor of the alternative would suggest that the mean height growth is more than 2 inches. Okay, it's called a one-sided hypothesis test here. The other example I just gave it on the slide is a two-sample hypothesis test. So in a two-sided hypothesis test, you might test, right, the null where it's equal to 2 instead of less than or equal to 2, and then bigger than or equal to 2. This is a two-sided hypothesis test. So let me, I guess, explain maybe the difference. Okay, so in the one-sided test, right, in a one-sided test, if I observe, so the one-sided test, 1, 2. I'll call this is a two-sided test. Sorry, this is a one-sided test. Maybe it's H naught mu less than or equal to 2 versus H1 mu is greater than 2. So in a one-sided test, if I have X bar equals 0, this is consistent with the null. Why? Because my sample average is below 2 inches, but it's maybe not consistent with a two-sided null, right? Because it's much less than 2 inches. Okay, those are the differences there. So here's more example, right? We can use X bar to test these hypotheses. If I have a one-sided test like this, then large values of X bar bigger than 2 favor the alternative. So favor the population mean actually being bigger than 2. So i.e. X bar equals 4. For two-sided tests, large or small values, so of X bar far from 2, favor H1. So for example, X bar equals 0 or X bar equals 4, both favor the alternative. Confidence intervals. So we're talking about functions, right? Functions of data. That means you just take your data, you plug it into a function, you get a number. So in R, right, you have these functions, mean, variance, standard deviation, length. All of these things are functions of actual data. So confidence intervals are also functions of our data. They're functions where we have two different sides. So you've probably heard a 95% confidence interval. Okay, it's from X to Y. Those are functions of your data. You actually plug your data into those functions and you get your confidence interval. So we have a lower confidence interval and we have an upper confidence interval. And the definition of a 1 minus alpha percent confidence interval, so if we're doing a 95%, alpha would be 0.05, okay, is that the probability that the mean value is between the lower value of this, the lower function value and the upper function value is 1 minus alpha. And that's based on repeated samples. So as an example, right, it's not saying for sure that it will contain that. It's saying, let's say I go out and I get 100 kids' heights, and I compute the lower confidence interval and the upper confidence interval. And then I go out and get 100 more kids' heights, and I get the lower confidence interval and the upper confidence interval. And I do that like 1,000 times. 95% of the time the true value of the average growth will be in those confidence intervals. Okay, not 100% of the time, but 95% of the time. So it's a repeated sampling thing. However, for your sample, this gives you a good estimate of where that true value is, right? So you might get a 95% confidence interval that says, okay, the lower bound is 1, the upper bound is 3. That means you have pretty good evidence that the true average growth from 7 to 8 years old is between 1 and 3. So again, right, the correct interpretation of a confidence interval. Say in truth, 7 to 8 year olds grow an average of mu equals 2 inches. If you go and collect data, you get a 95% confidence interval. And for example, this is just an example, you get data, and in your data, your lower confidence interval is 0, your upper confidence interval is 1. The true value, mu here, is not in that confidence interval. However, if we did this thousands of times, I went out and got a new data set, constructed the lower confidence interval, the upper confidence interval, over and over and over again. About 95% of the time, I would have my true population growth within these two values. Okay, broke. We're 95% confident that the true mean height growth is between 0 and 1. That's not a true thing. Woke is the estimated 90%, 5% confidence interval for the mean height growth is between 0 and 1. So don't talk about, hey, we're positive that this population mean is in there. It either is or it isn't, right? So in this example here, it's not in there. You could get a confidence interval that doesn't contain the true value. However, the confidence interval is constructed in a way that gives you some good information about where this thing might live. So you want to just say where the confidence interval is, but do not say something like, oh, you know, we're positive that we have a value, our true value is in there. Why are confidence intervals useful? They give us an estimate of where the true value of mu, in this case, height growth, true population height growth between 7 and 8 years old is based on our sample. They can be used for hypothesis testing, confidence intervals. If I construct a two-sided confidence interval and it doesn't contain the value 2, that also means I would reject the null of mu is equal to 2. And we'll see that later. I'll show you examples in the next kind of couple lectures. This is just a high-level conceptual idea of what confidence intervals are. The next couple lectures, we'll look at specific examples. They can get smaller as your sample size increases. So they do get smaller. So these intervals, right, if you have a smaller sample size, are going to be bigger. And as your sample size gets bigger, they're going to get smaller and smaller and smaller. And that kind of makes sense. You're more certain about where this value of mu lives. If you went out and you collected 10 kids' heights and you got an average of 2 inches, would you be certain that the average height growth between 7 and 8 is 2 inches? Probably not. But if you went out and you collected 1 million kids and measured their heights between 7 and 8 inches, and in those 1 million kids, they on average grew 2 inches, you feel pretty confident to say, hey, look, it looks like if you're 7 years old, you're probably going to grow 2 inches on average. P-values. Okay, so you're probably familiar with p-values, right? P less than 0.05 is a significant result. That's kind of the standard here. So a p-value is a function of your data. So you get a test statistic for some tests, and you should have seen some of this before, right? So t-tests, z-tests, all those things. You get a test statistic t. I say it here g because it's a function of your data, right? If you remember the t-test, right? The t-test, s is the standard deviation, is this right here. It's square root of n times x bar minus mu. That thing is a t statistic, right? This is a function of your data. This is the sample size. It's a function of your data. How big is the data? Standard deviation is a function of your data. X is a function of your data. And mu is a function of the null hypothesis that you want to test. You're probably familiar seeing Now, once you get a test statistic, the p-value here is the probability of observing an as extreme or more extreme test statistic in favor of the alternative if the null is true. So said differently, okay, if the null is true, the probability we get a test statistic that's favoring the alternative. So in the case we're talking about, right, testing mu equals 2. If mu is equal to 4, or the x bar is equal to 4, what's the probability, if the null really is true, that mu is 2, of observing x bar equal to 4, or something bigger, x bar equal to 5, x bar equal to 6, x bar equal to 7, x bar equal to 8, if the null is true. That's what a p-value is. That's the formal definition. In a way, it's not exactly this, but you can think about it as the probability that the null is true. So if that probability is very small, based on the data you have, you would suggest, right, that the null is false and reject it. That's why we have this kind of 5%. So if the probability that the null is true is less than 5%, generally that's how you say a significant result. And that's it. So we'll get more into hypothesis tests and confidence intervals in the next couple lectures. And if you have any questions kind of in general about these, I would say the first thing I would do is kind of watch the other lectures, lectures 2 and 3 in this section. And then I would come back to this section here as well, and watch it again. So again, the key thing I want you to know is hypothesis tests, right? We assume some kind of truth, and we assume some kind of difference between that. They have to have all sort of the realm of possibilities. And we plug in our data into a function, our sample data, and we use that function to test whether our null hypothesis is true or false. And that's the idea of hypothesis tests, and confidence intervals give us an estimate of where the parameter we want to test lives.